Guarantee that this is the only visual video of its kind on the internet, offering you an intuitive understanding of the concept like never before.
So just dedicate the 10 minutes and learn how should math be studied for lifetime. And if you feel the video slow, please speed it up. Now we will investigate the process of calculating all the possible ways of lining of 7 students such that no 2 girls are together.
A group of 7 students consisting of 4 boys and 3 girls arrange themselves in a single line. If their positions are determined purely by chance, what is the probability that no 2 girls will be standing next to one another? We designate the 4 boys as B1, B2, B3, and B4, and the 3 girls as G1, G2, and G3. Their positions in the line are to be imagined as follows. We know that probability is calculated as the following formula. Probability equals desired number of outcomes. Open, total number of outcomes. Now let us focus on total number of outcomes first. 7 students can be placed in any order along the line without any restriction. This means we need to consider every possible way they can be arranged. Since there are 7 students, we calculate the total number of possible arrangements by multiplying all the numbers from 7 down to 1, which gives us 7 factorial possible ways to arrange them. Here we have observed 4 possible arrangements along the line out of the total 7 factorial possible ways. Here are 4 additional examples of how 4 boys, B1, B2, B3, B4, and 3 girls, G1, G2, G3, can be arranged in a row.
These are just a few of the possibilities contained within 7 factorial.
In some of these examples, the girls are positioned separately, while in others, they are standing together. For instance, in the arrangements on the left, the girls are not grouped together, whereas in the ones on the right, they are placed together. Therefore, the total arrangements, as determined by 7 factorial, encompass both scenarios. One where at least 2 girls are together and another where no 2 girls are together. To identify all such outcomes, we place 4 boys into the 4 green slabs first. Then we now accommodate 4 boys into these 4 green slabs. Next, we insert spaces between each of the green slabs, as well as at the beginning and the end. In these spaces, we will place yellow slabs. The purpose of these yellow slabs will become clear shortly.
Now, we mark these yellow slabs, numbering them. The arrangement itself solves the problem. We will place the 3 girls on yellow slabs, which are already separated from one another by green slabs. Because of this natural spacing, simply choosing any 3 of the 5 yellow slabs automatically guarantees that no 2 girls will be positioned side by side.
That means we will place the 3 girls on the yellow slabs and the 4 boys on the green slabs. Since we have only 3 girls, so we select any 3 out of the 5 available yellow slabs. Because there is always at least 1 green slab separating each yellow slab, placing the girls on these yellow slabs ensures that no 2 girls are ever side by side. That means we have to choose 3 yellow slabs from 5 available yellow slabs.
The expression 5C3 takes 5 yellow slabs as input and generates 10 unique combinations, each consisting of 3 distinct yellow slabs. Here, once again, we've seen how 5C3 takes 5 yellow slabs as input and generates all the possible combinations of 3 yellow slabs. Altogether, this results in 10 distinct groups, each offering a unique selection from the original set. To ensure no 2 girls sit together, we first arrange the boys. This creates distinct spaces between and around them. We then place the girls into these available spaces, guaranteeing they are always separated. And these 10 possibilities are those where we will keep our 3 girls. To quickly justify how the 10 selection processes ensure no girls are together while arranging all 7, let's consider 3 examples. By ensuring no 2 girls are selected together in any combination, we strategically place the girls among the 7 individuals. We will keep slabs 1, 3 and 5 and remove slabs 2 and 4. Then we will place 3 girls into these selected slabs.
Now, let's observe the second example with the yellow slabs 1, 4, and 5. In this case, we will discard the unselected slabs 2 and 3 and then accommodate the 3 girls.
This way, by taking the second example also, we justify that the process of selecting any 3 yellow slabs out of 5 indeed results in a selection where no 2 girls are together.
Let us list some of the examples we have considered so far and permute them, meaning we'll interchange their positions to create new arrangements.
To explore the different ways to arrange 4 boys, let's begin with a simple example. We'll start by swapping the positions of B1 and B2. And this is the new valid arrangement. We will see another possibility arising by changing the position of B3 and B4. And this is the new valid arrangement. Okay, let's look at one last example of how to make a new lineup. This time, we're going to swap all of 4 boys' position. Ultimately, by continuing to swap the boys' positions, we discover that a total of 24 unique arrangements are possible. First, we made the boys change places with each other. We did this when the girls were standing on the yellow slabs numbered 1, 2, and 3. Now, we will make the boys exchange places again. This will happen when the girls are standing on the yellow slabs numbered 1, 3, and 5. Presumably, it still has 4 factorial or 24 possibilities, since we are interchanging the 4 boys again. Finally, we swapped the places of the 4 boys one last time. We do this when the girls are standing on the yellow slabs with the numbers 1, 4, and 5. This also gives us 24 different ways to put the boys in order.
Thus, for each of those 10 different situations, we have figured out all the possible ways the 4 boys can be arranged in a line. Since there are 10 ways to place the girls so they aren't together, and each of those ways has 4 factorial, or 24 ways to arrange the boys, we multiply them to get the total. So, 10 times 24 gives us 240 ways altogether. In the previous arrangements, we focused on swapping the positions of the boys while keeping the girls in the same spots. Now, to account for all possible variations of the girls' positioning, we need to interchange their positions as well. Since there are 3 girls in each of the 240 arrangements we've already obtained, we can arrange the girls in 3 factorial, or 6 different ways for each case. Therefore, the total number of possible arrangements is 240 multiplied by 3 factorial, giving us a final count of 1,440 possible configurations. In this process, we have thoroughly explored all the favorable possibilities and gained a clear understanding of the origin of each term. To ensure complete clarity, we have outlined once more how each term contributes to the final calculation. By examining the origin of each term, we now have the ability to visualize how each one arises in the process. In this manner, we have successfully completed the process of calculating the probability. Here, we have clearly presented all the findings we have discovered so far in an easily understandable way.
Anyone can feel lost in such a tutorial, but if you understand it, it covers many probability problems.
If you have watched so far, you are really amazing. I do really appreciate. Please subscribe channel since we are meeting again in next video. Thank you.